The corner point method, step-by-step process. Hello everyone. Today, we are going to dive into a very powerful tool in mathematical optimization known as the corner point method. Now, you might be wondering, what exactly is this method? Essentially, the corner point method is a systematic, algorithmic approach. Think of it as a step-by-step recipe that we follow to find the optimal value, which simply means the absolute best result, whether we are looking for a maximum value, like maximum profit, or a minimum value, like minimum cost. We use this when we are working with a linear objective function that is subject to a specific set of linear constraints. The real magic behind this method lies in a fundamental principle of linear programming problems, or LPPs. The principle states that the optimal solution, that perfect point we are searching for, will always occur at one of the vertices, which we also call the corner points, of the feasible region. In other words, instead of checking every single point in a shaded area, we only need to focus our attention on the corners. Below is the detailed, step-by-step process to solve an LPP using this method. In the next few slides, I am going to walk you through the detailed, step-by-step process of how to apply this method, from graphing your constraints to verifying your final answer. Let's get started. Step-by-step algorithmic process. Now that we understand the core principle, that the optimal solution always hides at the vertices, let's walk through the actual algorithmic process. This is the how-to guide for solving any linear programming problem. We begin with step 1, identifying the feasible region. Think of this as drawing the boundaries of our playground. First, you need to graph the inequalities. A helpful trick here is to treat each inequality as if it were an equation, which gives you a straight line to plot on your Cartesian plane. Once the lines are drawn, you need to determine the half-plane, or which side of the line to shade. A reliable way to do this is by testing a point, usually the origin 0, 0. If the origin satisfies the inequality, you shade towards it. If not, you shade the other side. Don't forget to apply non-negative constraints. In most real-world problems, like the production example we will see later, x is greater than or equal to 0, and y is greater than or equal to 0, so we focus our attention strictly on the first quadrant. Finally, find the intersection. The area where all your shaded regions overlap is what we call the feasible region. Every single point inside this overlapping area is a valid, or feasible, solution. Once you have that region clearly marked, we move to step 2, determining the corner points. Now that the playground is defined, we need to find the exact coordinates of its vertices. Start by identifying the vertices. These are the sharp corners where the boundary lines meet. If a corner point is easy to see, like where a line hits an axis, you can just read it off the graph. However, if a corner point is floating in the middle of the plane, you'll need to calculate its coordinates precisely. You can do this by taking the two equations for the intersecting lines and solving them as a system, using either the substitution or elimination method. With our list of corner points ready, we proceed to step 3, evaluating the objective function. This is where we test our candidates to see which one is the winner. Take the x and y coordinates from each corner point you found in the previous step and substitute them into your objective function, which is typically written as z equals a times x plus b times y. To keep your work organized and avoid the common mistakes we'll discuss later, I highly recommend you tabulate your results. Create a simple table with one column for the corner point, x and y, and another column for the resulting value of z. Finally, we reach step 4, determining optimality. This last step is crucial because your strategy changes depending on whether your region is bounded or unbounded. In case A, for bounded regions, your region is enclosed like a polygon. Because it's closed in, the extreme value theorem guarantees that both a maximum and a minimum value exist. In this case, simply look at your table. The largest value you calculated is your maximum value, m, and the smallest is your minimum value, m. However, be careful with case B, for unbounded regions. If your region extends infinitely, a maximum or minimum might not actually exist. To verify a maximum, if you find a potential maximum m at a corner point, you must check if the open half-plane, where a times x plus b times y is greater than m, shares any area with your feasible region. If it does, then z can grow infinitely large, meaning no maximum exists. The same logic applies to verifying a minimum. You must check if the area where a times x plus b times y is less than m overlaps with your region. If it does, then no minimum exists. Keep these steps in mind, as we are about to apply them to a practical production scenario in the next slide. Real-world example, production optimization. Now that we have understood the theoretical steps and the logic behind the method, let's put everything into practice with a real-world application. Imagine you are a carpenter running a small business. You produce two main products: tables, which we will represent by the variable x, and chairs, we will represent by the variable y. To determine your business strategy, we first look at your profit margins. Each table you complete yields a profit of $50, and each chair yields $30. Our ultimate goal, or our objective, is to maximize your total profit, which we can write as z equals 50x plus 30y. However, you can't just make infinite products. You are limited by your resources. First, we have a labor constraint. Each table requires 2 hours of work, and each chair requires 1 hour. You only have a total of 100 labor hours available. Second, we have a material constraint. Both tables and chairs require 1 unit of wood, and you only have 60 units of wood in stock. Finally, we must remember our non-negativity constraints, meaning x is greater than or equal to 0, and y is greater than or equal to 0, because you cannot produce a negative number of items. Let's solve this step by step, using the process we just discussed. First, we need to identify the feasible region. We translate our constraints into linear inequalities. For the labor constraint, we write 2x plus y is less than or equal to 100. To graph this, we find where the line hits the axes. It passes through the point 50, 0, and the point 0, 100. For our material constraint, we write x plus y is less than or equal to 60, which passes through 60, 0, and 0, 60. When you shade the area that satisfies all these conditions within the first quadrant, you get a closed, bounded area. This is our feasible region. Next, we must determine the corner points, or the vertices, of this region. Looking at our graph, we can clearly see 4 points. Point A is the origin, which is 0, 0. Point B is the y-intercept of the most restrictive constraint, which is 0, 60. Point D is the x-intercept of our other limiting constraint, which is 50, 0. But what about the point where the two lines cross? That is our point C. To find its exact coordinates, we solve the system of equations by subtracting the second equation from the first. 2x plus y minus x plus y equals 100 minus 60, which simplifies to x equals 40. If we plug x equals 40 back into our second equation, x plus y equals 60, we find that y must be 20. So, point C is 40, 20. Now we move to step 3, evaluating the objective function. We will plug each of these 4 corner points into our profit formula, z equals 50x plus 30y. At the origin 0, 0, the profit is 0. At point 0, 60, the profit is 50 times 0 plus 30 times 60, which gives us $1,800. At point 40, 20, the profit is 50 times 40 plus 30 times 20. That is $2,000 plus 600, resulting in $2,600. And at point 50, 0, the profit is 50 times 50 plus 30 times 0, which is $2,500. Finally, we determine optimality. Since our feasible region is bounded, we simply look for the highest value. As we can see, the maximum profit is $2,600. To achieve this, the carpenter should produce exactly 40 tables and 20 chairs. As we move to the next slide, keep in mind that while this calculation was straightforward, there are a few common pitfalls that can lead to incorrect results. Common mistakes to avoid. First, watch out for ignoring non-negative constraints. It is very easy to get caught up in the algebra and forget that x is greater than or equal to 0, and y is greater than or equal to 0. In real-world problems, like our production example, you can't produce a negative number of chairs. If you forget these constraints, you might accidentally consider points in the second or third quadrants, which are physically impossible and will lead you to an incorrect solution. Second, be extremely careful with incorrect shading. As we saw in Step 1, the entire feasible region depends on which side of the line you shade. If you see a less than or equal to sign, but you accidentally shade the side for greater than or equal to, your entire feasible region will be wrong, and every corner point you calculate after that will be incorrect. Third, a very important point regarding unbounded regions. Do not simply assume the highest value is the maximum. As I mentioned in the previous slide, when a region is unbounded, the values can sometimes increase infinitely. You cannot just look at your table of values and pick the largest number. You must always perform that open half-plane check to verify if a true maximum actually exists. Finally, keep an eye on calculation errors in intersections. Finding the corner points often requires solving simultaneous equations, such as when we found point C in our example. A small mistake in substitution or elimination will give you the wrong coordinates. My best advice is to always double-check your work by plugging your final intersection point back into both of the original constraint equations to ensure it satisfies both. Now that we have walked through the step-by-step process and seen how it applies to our carpenter example, I want to pause and discuss some common pitfalls. Even if you understand the theory, these specific errors can easily lead to the wrong answer on an exam. As we move to our final slide, let's quickly summarize the key takeaways to ensure you have a solid grasp of the entire method. Key takeaways. All right, we have reached the end of our lesson. Before you move on to your practice problems, let's quickly recap the key takeaways from today's session to ensure you have a solid grasp of the corner point method. First, remember the corner point theorem. This is the heart of everything we've discussed. It states that the optimal solution, meaning the absolute maximum or minimum value of a linear programming problem, will always occur at one of the vertices or the corner points of the feasible region. You don't need to test every single point in the shaded area. You only need to focus on those corners. Second, I want you to memorize this simple process flow. Whenever you approach a problem, follow these 4 steps in order. First, graph your inequalities to find the region. Second, find the vertices where those lines intersect. Third, evaluate the objective function, which we call z, at each of those points. And finally, compare the values to identify your winner. Third, pay close attention to the nature of your feasible region. As we saw in our step-by-step guide, if the region is bounded, meaning it is fully enclosed like a polygon, you are guaranteed to find both a maximum and a minimum value. However, if the region is unbounded and extends infinitely, you cannot simply assume a maximum exists. You must perform that extra verification step we discussed to check if the function can increase or decrease indefinitely. Finally, always keep the concept of feasibility in mind. A point is only a candidate for the optimal solution if it satisfies all constraints simultaneously. If a point fails even one inequality, it is outside the feasible region and cannot be your answer. Keep these principles in mind, and you'll be able to tackle even the most complex optimization problems with confidence. Great job today!